lesson. All right, so now we are on the last, let me type it in here. We're on the last review section, like I said earlier. So this is R8, and
Section 1.
I'll just call it this. It's not exactly called this, roots, and I don't know, let's just call it exponents. What's that?
You have something.
I know I do. I don't know what that is. Let's see. I don't know where that came from. All right. Let's turn it into the pen. Let's change the color of it. And let's turn that. Okay. Now we should be ready to go. Let's see if that works. Yep. All right. So we're going to do roots, like square roots. We've done a little bit of that earlier in the year, didn't we? Didn't we do a little bit of square root stuff? Okay. We didn't do too much of it, but we're going to do a lot of it in this section. All right. And it's not just square roots. We're going to do cube roots, fourth roots, fifth roots, and all that kind of stuff. So that's why it just says roots. And we're also going to talk about exponents. Not just any old exponents. Oh, let me flip this on so we can hear. All right. Not just any old exponents, but a lot of our exponents are going to be fractional exponents. Okay, I probably should have written it in there. I just didn't have enough room. Okay, or rational. Remember that word rational? We just did R7 on like rational, whatever it was called. So rational is the word ratio is in the word rational. And so we're talking about fractions. So we're going to be doing roots, like square roots, cube roots, and all that stuff. And we're going to do fractional exponents. So we're going to take things to like the half power, the 1/3 power, the 2/3 power, all kinds of crazy stuff like that. All right, let's talk about a root first of all. Let's just do this. Let's put that little symbol. That little symbol right there, sometimes people put like a little like that. Okay, but I'm just not as fancy as putting that little doohickey thing right there. I don't know what it's called. But anyway, I just write it like this. This actually has a name, and this is called the radical. Radical. Back in the 80s, when I was a teenager, that was like the phrase, you know, something was wild and crazy. We would say, well, that was radical. You ever watch movies from the 80s? And they might say radical. We actually used to say that. Or we would shorten it, of course, to rad. That was really rad. It had a very short lifespan, but the movies loved, you know, the 80s movies anyway. They always say rad, but I'm sure it didn't come from this. We could have something inside of that radical. So this actual symbol right here is a radical. It's not necessarily a square root. Not necessarily, okay? I'll talk about that in a second. But this little symbol itself is just called a radical. And then we would have a number inside of here. I'm just going to put a generic letter here just to represent any number at all. All right, and they give this a name. This is not quite as familiar, but they call this the radicand. Okay, not radicant, radicand do. Okay, anyway, sorry. So radicand. My math nerd is coming out in me. All right, and then you could have a certain root, depending on what the root is. It could be a square root, it could be a cube root, fourth root, fifth root, or whatever number. And I'll put a little letter there. I'll put a little, that's supposed to be an N. N, I guess. It doesn't look any better. But it's supposed to be an N. And we call this the index. I probably will not refer to these all that much, but it's just so you know what it is. Okay, so you basically got three parts to one of these roots we're going to talk about. You got the root itself, or the radical. Okay, you got the index, you got the radicand. All right. So for instance, if I just had this, if I had, and we've done this before, I'll start off with about the easiest one of the easiest ones you can do. If I just have a radical symbol and a radicand, which is 4, what's the index? If there's no number out here where the n is, what can you assume it is? No? It's 2. Why? Because it's a what? It's a square root, okay? You would assume that that's a 2. You could put a 2 there if you wanted to. What does that actually mean? It means what number multiplied by itself. So how many numbers? One number and itself is how many numbers? 2 numbers. What number times itself is equal to the radicand, the number inside of the root? So what would that be? That would just be a 2. You could also have something like this. Put a 3 out there. Now this, you're asking yourself, what number multiplied by itself 3 times? You understand why 3 times? Because that little 3 right there, that little index tells you what single number multiplied by itself this many times. All right? So 1, 2, 3 times. So you got a number times itself again is going to equal 8. So what is that?
2.
It's a 2. And that's one that you should just recognize very, very easily. We recognize a lot of square roots. Let's go through some of the square roots real quick that we know, we recognize. Let's kind of go in order. Square root of 4 is 2. What would be the next square root that comes out even like that? Square root of 6? A number times itself?
I'm sorry.
No, you can't get a number times itself that's equal to 6. Not an integer anyway, not a rounded whole number. Okay, 16, but there's one in between. 9, right. So you could have the square root of 9, which is 3. Now you have the what? Square root of 16, which is what? 4. Square root of what would be the next one? 25, okay? You should recognize all of these, okay? You should just look at it and bam, you know it already. Now, when you get cube roots, fourth roots, fifth roots, and all that kind of stuff, that's a little bit different. What if you had this? What if you had the fifth root of 32? So what does that mean? It means what single number times itself 5 times is going to give you 32. So pick a number that this number times itself, times itself, times itself, times itself is going to be 32. 2 is, right? Okay, I just picked easy ones. They all happen to come out to 2 here. But 2 times 2 is what? 4 times 2 is 8 times 2 is 16 times 2 is 32. All right, so again, understand what you're asking yourself. You're asking yourself what number times itself this many times is going to be this number right here. Well, 2 is. So 2 to the 5th is equal to 32. Would you agree? All right, so it's good that we start with this. It's pretty basic stuff, but it's good that we start with this so we understand what that index is doing, what the radicand is, and all that. Yeah.
So does it have to be like on the very far top?
Yeah, it's here. Let's make it a little bit bigger.
Or does it have can it also be just at the next to it?
Let's make it really big. Okay, so if I had a 16 in here, and then we had a
So that does
4 right there. It's got to be small, and it's got to be kind of tucked in that little elbow of that radical. Okay? Don't put it like this. If you did this, that means something completely different, doesn't it? What does this mean? It means 4 times what? The square root of 16. Okay? This is completely different. You with me on that? All right? It's little, okay? It's smaller, and it's tucked inside of here. All right? Sometimes I'm a little sloppy with that, but make sure that this number is considerably bigger than this one right here. Okay? The radicand is considerably bigger than the index. All right? Now, again, we all write pretty fast. We get a little bit sloppy. But make sure, if you mean the 4th root of 16, you don't make it look like this. This and this are completely different.
All right.
We good?
Yep.
All right.
Thank you.
So now, let's do a couple examples. Yeah, let's do this. And I'm going to show you, I don't know if I call it a trick, but I guess we'll call it a trick. So this just says simplify. All right, these first ones that we're going to do right here. And we've already done this, but we're going to put it in again because it's one of our official examples. That's a little 3 right there. Now, I want to show you something. You could just figure this out. You can do this in your head, okay? So what number times itself 3 times is equal to 8? We've already done it just a few minutes ago. What is that? It's 2, okay? But I'm going to show you something else. Sometimes this can be helpful. So I'm going to write sometimes when I write small, this doesn't work too well. There we go. So the cube root of 8. So what I could do is I could write 8 with a base and an exponent. How could I write 8 with something to another power?
2 over 8.
2 over 8 is not 8.
2 over 4.
Peyton, how can I write this with a base and an exponent? 8. I just want to rewrite it. Something to something power is 8. What is it? Well, 4 times 2 is 8, but it's not to a power. I want something, a base, to a power. Josiah? 2 to the third, okay? I could have 2 to the third. Would you agree 2 to the third is the same as 8? Okay? Now, watch what's going to happen here. Anytime you have something that's cubed inside of a cube root, guess what happens to the cube root and the cubed? They basically cancel each other out. Okay? They undo each other, some people say. All right? They kind of cancel each other out. Would you agree with that? So sometimes it's pretty helpful to write it, that number right here, if you can figure out what it is, a base to a power. And if it's the same power as what this index is right here, you can say that this cube root cancels with this cube, and you just have what's left over. For instance, if I had x to the fourth, and I was going to take the fourth root of x to the fourth, it would just be what's left over. So what happens here? The fourth root cancels out with the 4 exponent, right? The fourth power. They undo each other. They cancel each other out. What are you left with? Just the x, okay? Not just a 1, but an x. You're left with that. Here's another thing you could do. What if you had, let's just do square root. What if I have the square root of x to the third? This is the square root. Again, if you don't put a little number in that little crevice of that radical, it's automatically a square root, okay? Because it happens so much. We use square roots so much that they decided, let's just not even put the 2 there, all right? We know what that means, all right? So how in the world would you figure this out? Well, what you could do, remember, this is the square root, okay? So what we could do is we could take x to the third and rewrite it so that at least something cancels out. Very good. Very good. Okay? Do you see that? So x cubed is the same as x squared times x. Why in the world would I want to write it like that? Because the square root, I'll put the 2 there just to remind you, the square root cancels out with what? This squared. But you got to be careful. What's left over now? This is just left over to be an x, but you still have something else. What do you still have, though? You still have another x, and it's underneath a what? A square root. Everybody see that? So this x just comes out by itself. But this one right here is still inside the square root, so we still have to keep it inside the square root. So that's how you would simplify that. So that's going to come in helpful a little bit later on, all right? Just kind of, I actually got a little ahead of myself, but I knew that was coming up, so I figured I'd throw that in there. We'll get to it. We'll see. We'll do another example on that, all right? Let's do another one. Oh, now, if you look at the book, they go through some fancy stuff at the beginning, and they put some absolute value stuff in there. I thought that might confuse you more than anything, but if you have the book open, if you look at it, do you see kind of like the definition of square roots and stuff? They say, like, if the index of this thing right here is even, then you got to put a absolute value. If it's odd, you don't have to put an absolute value. Josh, you see that in there? Yeah. Okay, what page was that on? 72. All right, so if you look on page 72, because I don't have the book out in front of me, I just have my notes here. So if you look at it, you're going to see some kind of weird stuff. But I thought about going over that with you, but I thought that might just be way more confusing than anything, so I'm just going to show you. So watch this. What if you have the cube root of, watch this, negative 64? Well, first of all, let's forget the negative right now. Let's just think 64. So what's the cube root of 64? Like in our head, let's go through something. You know it's not going to be a super big number. You know it's not going to be 2, right? Because 2 times 2 times 2 is 8, all right? What about 3? Does the cube root of 64 equal 3? Now let's try 3. 3 times 3 is what? 9 times 3 is 27. That doesn't work. Let's try the next one up. What's the next one up? 4. Let's try 4. 4 times 4 is 16. 16 times 4 is 64. So 4 works, doesn't it? But we have a negative right here. So what we're asking, again, what times what times what? 3 times. Something multiplied by itself 3 times equals negative 64. Is it negative 4? Let's try it. Negative 4 times negative 4 is positive 16. times another negative 4 is negative 64. Does that work? Absolutely. I want to show you something. You can take the cube root or fifth root or seventh root or ninth root. What are all those numbers? What kind of numbers are all those? They're all, what did you say? I didn't hear what you said. Odd. You did say odd. Okay. I thought you said 5. I didn't. Okay, odd. That's correct. If you have an odd index or an odd root, you can take an odd root of a negative number, and it's going to come out negative. Okay? Can you take an even root of a negative number? For instance, we'll just do square root, and we'll put a negative 16 in here. Is this going to be negative 4? Because what times itself is negative 16? Nothing. Because if I multiply two numbers, if they're both negative or they're both positive, what's my answer always going to be? It's always going to be positive, isn't it? Can I get two of the same exact numbers to multiply together to be a negative anything? No, I can't. So can you do this? You cannot. So anytime you have an even index or an even root, you cannot take an even root of a negative number. Does that make sense? All right, just make sure that you understand that. So if I had a fourth root or a sixth root or an eighth root, you cannot take an even root of a negative number. We good with that? Okay, so that's pretty important. Let's do a couple more of these. This is example C. This is example 1, by the way, and this has got 4 parts to it. So it's the fourth root. Now we're going to get really crazy. Look at this. Now they stuck a fraction inside of this root. So what in the world are we going to do with this? Well, I could approach this a couple different ways, or you could look at it like this. Here's what the book does. They haven't shown you the rule that I would probably do. Like if I was going to do this from scratch, I probably wouldn't do it the way the book does it right now. Okay, we're going to learn a rule a little bit later that we can apply here. But this is what the book does. What they decide is, let's write 1 over 16 to a fourth power. Can we do that? Can we write 1 over 16 as something to the fourth power, so that the fourth power and the fourth root will cancel each other out? That's what we're trying to do here. So can you do that? 1 over what to the fourth power? What do you think? 2. That's right, because 2 to the fourth is what? 16. So 1/2 to the what? Fourth. Would you agree that that's 1 over 16? All right, so it took a little bit of thought. All right, but again, these are rigged for you, right? They make these so they come out kind of easy, at least at the beginning. All right, so when I'm looking at this and I see a fourth power, I'm thinking, you know what I could probably do? I could probably take what's inside of here and take something to the fourth power so that the fourth root and the fourth power cancel each other out. And we could, right? Again, they rigged these for you so that we could do this. So now what can you do? That fourth root and that fourth power, what do? They cancel each other out. What are you left with? 1/2. Let's check it. What does this mean? This means I need a number. If I multiply it by itself 4 times, it's going to be 1/16. Is 1/2 times itself 4 times 1/16? Sure it is, because it's 1/2. I'll just do it instead of putting my fingers up in the air. People online can't see that. All 3 people that are going to be watching this video. All right, so watch. This is our check to see this. Okay, it's 1/2 to the fourth power. So 2 times 2 is 4, times 2 is 8, times 2 is 16. So that's 1 over 16. Is that? Of course it is. So yes, it works. We good so far? Let's do another one. Okay, this time it's going to look a little weird. So this is to the -6. And then I'm going to put a -2, but the -2 is in parentheses. That's really important. And that's to the 6th power. Did I put -6 here? That was dumb. It's to the 6th power. I was thinking ahead to that -2, and I wrote that as a -6. Remember I said you can't take an even root of a negative number? Well, technically, it looks like a negative number, doesn't it? Yeah, it's a -2. Sure it is. But what's that -2? What's happening to that -2? It's taken to the what? 6th power. So anytime I take a negative number to an even power, what's it always going to come out to be? What kind of number? It's always going to come out positive, isn't it? All right. So technically, it looks like there's a negative inside here, but really, if I was to multiply that out, do we really have a negative inside the square root? Not really, because it's being taken to the 6th power. You with me on that? So really, it's a positive number once I take it to the 6th. But what can I do with this root and this exponent? That's the 6th root, and that's the 6th power. I can get rid of it, and what am I left with? I'm left with a -2. But the problem is, I can't take an even root and come out to a negative number. All right, so what they do, and this is what I was referring to before in the book, they get a little fancy. I didn't want to go through it too much, but we got to go through it right here. So when you can't take the 6th root of a negative number, so what they do is they say, by definition, it's the absolute value of that number. And so what would we get right there? The absolute value -2 is just 2, and that's your answer. Okay? So even though it looks like they cancel out and we're left with a negative, you actually have to stick it in absolute value and you get a positive. I know that's kind of weird. Let's just move on from that. Example 2 is showing you how to do it on a calculator. I'm not even going to give those to you on the quiz or test on this stuff. Okay, so I'm going to skip example 2. Let's go to example 3. Okay, so example 3. This is called simplifying radicals, if you want to write that down. I'm not going to just for the sake of time. So here's a few rules. And I think they might show you the rules, and in my notes I didn't write down those rules. I'll tell you what, before we do example A, let's do this. If I have this, m times n, they may use different letters in the book. I'm just doing this off the top of my head, okay? So if you have something like this, you have the square root, and you got two things that are multiplied times each other, there's a rule that allows us to do this. There's a rule that allows us to split both of these up underneath of its own square root. So let me just show what I'm talking about. So the rule says I'm allowed to do this. So instead of one big root with two things being multiplied, I could split it up so I have two separate roots that are being multiplied. See what I just did right there? All right. So for instance, if I had the square root of 3 times 2, how could you rewrite this? You could write it the square root of 3 times the square root of 2, and it's the same thing. And you could go the other way, right? If you had this, you could always get to that. Does that make sense? You're going to see why we're going to do that here in a second. So now let's do the actual example. So A. So this says the square root of 32. Now, first of all, are there two numbers that multiply together to be 32? What times itself is 32? 6? No. 6 times 6 is 36. 5 times 5 is 25. But they're not the same number. They got to be the same number. Okay, the square root, you got to multiply the same two numbers together to get 32. 16 times 16? No, that's a big old huge number. That's not 32. So would you agree there's nothing, is there? Okay, no integer. You know what I mean by integer? Like a rounded kind of whole number like that. Okay, so there's no, we'll just say whole number that multiplies, two of the same numbers multiplied to be 32. But we can still simplify it. So what we're going to do is this. Let's break it down into something that you can take the square root of. You can do this several different ways. Well, at least two I can think of. So what times what is 32? Now, not the same numbers, but just anything. What times what is 32? 8 times 4 is, okay, and that's okay. What's another one? 16 and 2. Let's do 16 and 2. Why did I pick 16 and 2? Because I know what the square root of 16 is. What is it? It's 4, isn't it? Okay. So I could have picked 8 and 4, but then you'd have to do like 2 steps. This way, I can just do 1 step. So what I can do now is this. I'll use this rule right here. I forget what they call it, product rule or something. I don't even know what they call it. It's just a simplifying rule. So what I can do, I'll apply this rule, that says I can split these up into their own individual square roots. You with me on that? See, that's the m times n. And so what did I do? I broke it up into the square root of m times the square root of n. And now let's take a look. What's the square root of 16? I know what that is. That comes out to a nice whole number. What? 4. Can I do anything else with that square root of 2? No. So I just leave it the square root of 2. So the square root of 32 is the same thing as 4 times the square root of 2. Same exact number. If you stick it in your calculator, you'll get the same decimal number. It won't come out even, but it'll come out to some decimal. And the decimal keeps on going forever and ever. Okay, we call that an irrational number. All right, it just keeps on going. It doesn't stop. Name me an irrational number that keeps on going forever. Yeah, but one that's that we use in geometry. Pi, 3.14159, blah, 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 and it's dot, 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 because it keeps on going forever, okay? And pi actually never repeats, okay? 1/3 is not irrational. 1/3 is rational because it repeats. Anytime you have a repeating decimal, then that's a rational number. That means we could write it as a fraction. If it doesn't repeat, okay, and it gives you all these random numbers after, it's called an irrational number, okay? You can't write it as a fraction, all right? So anyway, let's keep going. I got a little bit more to do. Let's do this one. Cube root of 16. Now, I know the square root of 16, 4 times 4, right, is 16. But the cube root of 16, wow, not sure. So what are we going to do? Let's break 16 down into what? You could go 4 times 4, but can you take the cube root of 4? No, but I could, excuse me, but I could write this as what? Man, gotta get rid of that COVID. I'm just kidding about the COVID, by the way, just in case anybody's. All right, so what do we got here? I just got a little tickle in my throat, that's all it is. All right, so what can we do here? I can do the same thing as I did with the square root, but I'm going to do it with a cube root. So watch. So what do you think this is? The cube root of 8 times, talk to me, cube root of 2. See what I did? Did the same rule, except I have a cube root this time instead of a square root. Okay, this works for any roots. So we know what the cube root of 8 is. We've done this a couple times already today. What's the cube root of 8? It's just plain old 2. Can we simplify the cube root of 2? No. So we write it. Now you got to be careful with this, okay? Because you don't want that 3 looking like it's being multiplied by that 2. Make it little, put it right next to that little radical, and put a 2 in there. So you're probably thinking, well, that looks a lot better than that does. Well, this is simplified, though, because we could take a root of something that's in there. So that is simplified. All right? I'm going to skip to D, just for the sake of time. You'll probably want to look at C on your own. But this time, we're going to throw in fraction. Remember that rule I showed you about that M and N thing? Well, the same thing works with division. So watch. I'm going to show you another rule now, since we're going to use that on this example. What if you had something like this? You had this m over n, and everything's underneath of that square root, or any root. It could be any root, okay? So what do you think we could do with this? If they were multiplied under one big square root, we broke them up into their own square roots, and we multiplied, right? So what do you think you're going to do here? You're going to separate them and put them under their own square root, and then divide. That makes sense, doesn't it? If that multiplication one makes sense, this one should make sense. This was what I was actually talking about just a little earlier. I said I would probably approach that one problem a little differently. Remember that 1 over 16, that square root of 1 over 16 thing? Okay. So this is what I would probably apply. So what can you do here? Watch, I'm going to write the numerator with a 4th root, and I'm going to write the denominator with a 4th root. Okay, just like we did here. So it looks a little ugly. And sometimes these do look really ugly. But you just take your time, remember your rules, and you should be okay. Well, it's supposed to be a 4. There we go. It looks a little better. And then an 81. So that's the first thing I would do on this. That's not too hard, is it? You see a fraction under a square root or any root, okay, fourth root in this case, then you can just split it up like this. So now what we're going to do is let's take the top one, this numerator, and let's do something with that. Is there any way that we can write 16 so it has a power of 4? Is there anything to the fourth power that's 16? And why do I want to the fourth power? Why did I say that in the first place? Because this is a fourth root, and it'd be really nice if my fourth root would cancel with my fourth power. Do you agree? All right, and again, I said these are rigged. All right, so there is going to be something. So what is it? We've done this a couple times already today. It's 2 to the fourth. So if you wanted to, you could write it, excuse me, 2 to the fourth. What about x to the fifth? Is there any way we could write x to the fifth having a fourth power in there somehow? I could write it x to the fourth what? Times x. That's supposed to be a dot. There we go. We kind of did that a little bit earlier. All right, what about this? 81. Is there anything multiplied by itself 4 times is going to give you 81? Try 3. 3 times 3 is 9. Another 3 times 3 is 9, right? That's 4 of them. And so the square root of 81 would be 3 to the what? Fourth. If you just wanted to do that in your head and just put down 3 right there, that's perfectly fine. I'm just showing you the step. All right, now let's see what's going to happen here. Let's apply that first rule, that multiplication rule with the m and n. So, whoops, I don't need that big old thing. Let's do this. Let's do the fourth root of 2 to the fourth. Now, you should be able to get to a certain point where you can do some of this stuff in your head. I'm showing you every little tiny step so that you know what we're doing. All right, so what's the next thing? So I took care of the 2 to the fourth. Now I'm going to go to the fourth root of what? X to the fourth. And then I'm going to go to the fourth root of just x. See what I did? I just took everything inside of that big square root, or not square root, but fourth root, and then broke them all into their individual fourth roots. That's what that first rule said that we did. This right here, we just do it, can't we? That and that cancel. What are we left with? 3 on the bottom. Now, that's not our final answer because we can simplify some of that stuff on the top. The whole reason why we did this is so we could simplify. So what happens here? That fourth root and that fourth power cancel out, so I'm left with a 2. What happens here? That cancels out. I'm left with an x. Can you cancel anything out here? No. So you have to write, don't forget the fourth root of x. So that's all you can do to the top. The bottom's already simplified. That's your answer. Looks ugly, looks weird, but that's it, simplified. All right, let's do some more. You can look on the video if you need to slow that down a little bit. What we're going to do is we're going to combine like terms now. Do you remember this stuff? What's 2x plus 3x? Talk to me. 5x, okay, because you added like terms, correct? They got to be like terms. Radicals can be like terms as well. So, for instance, I'll just do one that they don't do as an example. So if I had like 3 times the square root of 2 plus 5 times the square root of 2, what's that going to equal? It's going to be 8 times the square root of 2, right? Think of this as a variable. It's not a variable. It stands for a particular number, but think of it as a variable. So I got 3 of these plus 5 of these gives me what? 8 of these. You with me on that? You could have real crazy stuff. You could have 3 times the square root of x minus 1 plus 9 times the square root of x minus 1. What if I ask you to add those two things up? I got 3 of these. I got 9 of them. So now, how many do I have altogether? I got 12 of these. Minus 1. You with me on that? Okay, so we can add like terms even if we have radicals and roots and all that kind of stuff. All right, so let's do this example. Tell you what, I'm going to do example B. So this is example 4B. Again, just due to time. I'm going to skip the A one. So let's do this. This is the cube root of 8x to the fourth. Now, while I'm thinking about it, I probably will not be able to get to the 5th example because we only got a few minutes. So what I'm going to do is I'm going to make another video later today, and I'm going to put it up there, okay? You don't have class tomorrow, so I'm still going to give you the assignment and all that, but I'll put the next example up there so you can see it. So it's your responsibility to watch that at home. But let's try to finish this one up. And if you guys came in late, I gave a lesson plan thing out, so make sure you get that from me. That's the first time I've done that. I don't know if I'll do it every week, but at least I did it this week. So it's the cube root of 27x. All right, here we go. Let's go through this kind of quick. Let's break this down so that I can have something to the third power. So put a root out here. So 8 I can write as 2 cubed. X to the fourth I could write as x cubed times x. All right. Now, this negative x is actually a negative 1. So what I'm going to do, I'm just going to write it negative 1 times x, just to make it a little bit easier for us to see. 4 times the cube root of 27. 27 I can write as 3 cubed. And then you just put an x right there. So let's see what happens. Well, let's break them down. Oh, I only got 2 minutes left. Let's see if I can do this quick. So the cube root of 2 cubed. You could probably do this in your head. I'm just going to show you the steps, though. And then you got the cube root of x cubed. And then you got the cube root of x plus. This would be the cube root of negative 1. And then the cube root of x plus 4 times this cube root of x. What happens here? Cube root, that cancels. I'm left with a 2. That cancels. I'm left with an x. And then you got the cube root of x plus. What's the cube root of negative 1? What times what is negative 1? Well, it's negative 1. So it's negative. You can put a 1 there if you wanted to. Like that. Let's do this. This is 4. What happens here? That's a 3. Let's do this in our head so I don't have to write another step. What's 4 times 3? It's 12, right? And then the cube root of x. So now look, I got a cube root of x here. That's supposed to be a cube root. I got a cube root of x here, and I got a cube root of x here. So I got like terms, don't I? So I got a 2x, and then minus 1 of these plus 12 of these, all right? What are my like terms? Is this a like term with this? No, because this is a 2x. This doesn't have an x out in front, okay? I'm almost done. Just hang on. Don't pack up yet. So this is going to be 2x times the cube root of x. What's this going to be? This is a negative 1 plus 12, which gives us plus 11 cube root of x. That's the like terms right there. Okay, we added the like terms. This is not a like term. Okay, so we have to write it just like this. I would just keep it like this. The book writes it like this. They factor out a cube root of x. Okay, the book writes it like this. I would be perfectly fine if you just kept it like that. All right, you have the, I'm going to write it down here, but you guys can leave. You have the lesson plans. If you didn't get one, come up here and get one. I do want you to do those problems. And then example 5, I will do today sometime. Put it up on YouTube, and you can watch it tonight.
Please.
Mark, I got to have grades done. And I got to have the report card. Do you have a study hall tomorrow?
Yeah.
All right. You got to do it during the study hall then.
Thank you.
Oh, let me put the homework. So it's section R.8 part 1. It's pages 77, 78. And it's 7 to 53. A lot of people are not getting these lesson plans, and you guys came in late. Why is nobody picking up these lesson plans if you came in late? All right, that's the lesson, and that's done for today.